Hello and welcome everybody. This is the MATLAB and Simulink Racing Lounge. In today's episode we are going to talk about modeling vehicle dynamics, and for that episode I'm really glad to have two guest presenters on board. So hello Sebastian, hello Swarooph.
Hi Christoph.
Hi, Christoph.
Cool, so some of you might already know Sebastian from a previous episode on plant modeling. But anyway, would be cool if you could introduce yourself briefly.
Okay, so hi again everybody, I'm Sebastian Castro and I'm a training content developer for modeling and simulation tools.
Hello everyone, my name is Swarooph and I'm a content developer for student competitions.
This brings us directly to today's agenda. So we will mainly base our episode here on demos. So Swarooph will give you an introduction to a longitudinal vehicle dynamics demo and to a demo covering 3D suspension modeling. Then we will wrap up a bit on physical modeling and the tools you need to do so Simulink and Simscape. And at the end, we will let you know how you can learn physical modeling by announcing our online training. And this is the point, Swarooph, where I'm directly handing it over to you. Really looking forward to the software demonstrations.
Thanks Christoph. What I'm going to do now is move on to our demo model here. So we have an electric vehicle model here modeled using Simscape. I'm going to go ahead and simulate this model.
So while this model is running, I see some line colors that aren't really typical of Simulink. I see some green, some blue. Could you explain what's going on while this runs?
Yes, so that's a good question. The different colored lines here represent different domains. For example, the light green color on the right hand side represents the mechanical domain. The blue color on the left hand side represents the electrical domain. So here you see a battery pack system, which is an electrical domain, and you have a mechanical system here, for example the gearbox that we have, which connects the DC motor to the rest of our transmission system here. So let's go ahead and take a look at our results here. So here we see that the speed of the vehicle keeps stepping up, and then at some point it reaches a steady state speed of 40 kilometers per hour. And it stops at 40 kilometers per hour because we are actually controlling the speed of the vehicle here using some sort of a controller.
So PI controller, that's something that's commonly used. That's nice. So why is it then that it looks like the speed reference goes from 40 kilometers per hour down to some value of 5? How come you see other things going on here? Like I see the speed is going up in 3 sequential steps.
Yes. So you can see the 40 kilometers per hour to 5 kilometers per hour here, right? Apart from that, you also see these steps, and that's what Sebastian is asking about, and that is the effect of gear changes on the vehicle. So the different gear changes result in the different steps in the speeds here.
Okay guys, this leads me directly to a question. So how can you model gear shifts?
Yes, so let me go back to the model here. So here is a gear subsystem, and this is how we model gears. We are using multiple clutch blocks directly from Sim driveline, and we also have gearbox blocks to specify for that particular clutch what is the gear ratio. And we can use some sort of a logic in order to model our gear shifts. In this case, it's just an open loop logic. So we have our gear shifts specified using a signal builder, which can be used to interactively model custom signals. So here we have gear 1 for the first 10 seconds, gear 2 for the next 10 seconds, and gear 3 for the next 10 seconds. So if you go back to our scope here, you can also see that for the first 10 seconds you have this speed, and then it steps up, and then it steps up to show the gear changes.
Okay. So right now you're just feeding in the gears as things that happen at a certain time, but you could always make this a bit more intelligent, right?
Yes, you're right. In this case, the controller just controls the speed by monitoring what the throttle is going to be. We can also have a more complicated controller where the controller can also control the gear shifts and brakes as well.
Swarooph, let me ask another question. So what we see here is a battery pack and a DC motor. Would we also be capable of modeling a combustion engine where they're using that kind of modeling approach?
Yes, definitely. So let me open up our Simulink library browser here. So these are all the blocks that will be available, and we are using the Simscape library. And under Sim driveline, if you go to engines, there's a generic engine block which you can use to model your engine based on data that you get from your engine as well. Right now, this is an electric drive car, so you see DC motor.
Okay, perfect. We haven't mentioned that before, but the software tool you are using it is Simscape. We have seen that it's capable of doing certain domains, so we can model electric domains, mechanical domains. Are there also other domains that we can model using that tool?
Yep, definitely. So here we are using Sim Driveline, which can be used to model powertrain and other things like that. We also see other types of domain here. For example, you see pneumatic, thermal, hydraulic. So, and apart from that, we also have specialized add-on products, so you can model more complicated circuits using Sim Electronics. And Sim Hydraulics has some built-in blocks like hydraulic cylinders, and you have orifices and things like that to model hydraulic systems as well.
So I could throw in hydraulic actuators into my car model, which I think is pretty cool.
Yep. So for example, if I go into the gear subsystem here, we have different actuators for the clutch. Right now, these are just ideal actuators, so they are just applying signals. Instead, you could model some sort of a mechanical hydraulic system as well, which will model the actuator themselves.
Perfect. So I think guys watching that video start to see the beauty behind Simscape, and maybe you guys see the applications that are close. So you could do lap time simulation, you could model energy consumption. So it's pretty impressive what we've seen here in that short demo. Thank you very much, Swarooph. And I've heard that you have a second part of the demo, right?
Yep. So those are some of the applications that could be extended for this particular model. Let me show you another model which extends another application. So I'm just going to go ahead and simulate this model first. And let's go ahead and take a look at this other window here. So here we have a suspension system. So assume that this cylindrical component here is the wheel. And you also have a couple of arms, and you have a cylinder damper system here attached to, let's say, some sort of a car chassis. What we are looking at here is we are doing an open loop test by applying force at the contact patch for the tire and seeing what will be the effect of that force on our suspension system here.
So where's that force coming from then? Like, or where is it being applied?
Yep. So I'm going to go back to MATLAB for a second. So here I have a mat file. So if you have used MATLAB before, this is the data file that you use for MATLAB. So, and you can see that here I have a position input, and I'm directly importing this into our Simulink model. So if I go back to our Simulink model here and go inside the test force subsystem, I'm using that variable directly in our from workspace block here, and using that to feed in the force into the system.
Awesome. So you already have all this data in MATLAB, but if you had this in an external file like an Excel spreadsheet, or you're collecting this from some device, you could similarly do the same because you've got MATLAB behind all of this.
Yep.
To do it right.
So this is directly in a convenient format mat file which MATLAB can read. If you wanted to use data from an Excel file, importing data from an Excel file is also really easy, and maybe Christoph can point us to one of our Racing Lounge videos which talks about.
Yeah, we've had an episode on plotting, and there we've also plotted data that was initially stored in a text file and a Nexus spreadsheet. That's classic MATLAB application. So Swarooph, let me ask another question. If you go back to the highest level of that model, so the blocks here look again a bit different to what we are used to compared to Simulink. So what kind of software tool are we using here? Is it again Simscape, or is it a different add-on here?
It is a different add-on. So let me open up our library browser here again. So here we have Simscape, and there are several add-on products built on top of Simscape, and here we are using Sim Mechanics, which is used to model 3D bodies.
So that's where you get the animation from, right?
Yep. That's where the animation is also from.
Okay, so let me ask again a question. What could be a nice use case for Formula Student teams out there? What can they do by having modeled their 3D suspension?
Yep. So one of the things you can see here is, let me go back to our animation here. So I have this particular assembly configuration. So what will happen if one of these arms was smaller? What will happen if, let's say, the damping coefficient of this particular assembly here is smaller or larger? So if you wanted to do design of experiments like simulations, you can easily do that. Let me show you a quick example for that. So I'm going to go back to MATLAB here. So all the parameters that we are using is defined in this MATLAB file. So you can see the chassis dimensions, you have the arm lengths. So let's go ahead and change the length of this arm. So I'm going to increase this from 30 to 35 here.
How do you know what 35 was? So what units are you using right now?
So here we are using it in centimeters. Let's go to our model here. So if I access the ARM1 subsystem and the ARM block here, so we are using a MATLAB function to generate the cross-section of this particular component. So in that particular MATLAB function call, I'm using this ARM1 length variable. So, and that is in centimeters.
Okay. Well, perhaps worth a comment at that point. So we have a Racing Lounge episode on CAD import. So if you don't want to model all the components from scratch and just in sim mechanics, you definitely have the opportunity to import assemblies, import parts from your desired CAD platform. And we have a lot of valuable information for you in the respective episode.
Yep, that's a good point, Christoph. So let's go back to our animation here. So now, this was how it looked at 30 centimeters. If I update the diagram by hitting this button here, you will see that this becomes longer, right? And now we can simulate the model again to see what the effect of making that arm longer would be. So one of these quantities that you could measure is the position of the wheel with respect to the ground. So let me go back to the model here. So here under the test 4 subsystem, I'm measuring that in this particular scope. So you can take a look at this here. So based on our varying force that we apply, this is the position that was measured for this particular assembly.
Okay, and I think this is the point where guys watching the video can see the beauty of modeling a suspension in sim mechanics. You can plug all the optimization tools in MATLAB to that model. You can run several tests, optimize that, and finally you're capable of designing an optimal suspension for certain track conditions, optimal suspension for your car. This is definitely a helpful use case.
Yep. So let's suppose in this case we would like our displacement to be between 8 and 9 centimeters, right? So in this case it's above that particular constraint, and we could use optimization tools from MATLAB in order to come up with the right arm length that will give us a position between 8 and 9 centimeters in this case.
Perfect. Great. Thanks a lot, Swarooph, for introducing us to these two interesting software demonstrations. Now I think it's time to move on.
Yep. So I'm going to hand it over to Sebastian here. He's going to talk a little bit about the basics of what is Simulink and what is SimScape, etc.
Okay, thanks, Swarooph. So you've seen a couple examples of models using the SimScape tool. We just saw the longitudinal dynamics system in the context of an electrical vehicle. And also we just saw the three-dimensional suspension mechanism. I'll talk to you a little more about what is the technology that we just saw. So to start, I want to introduce you to two types of graphical models. The first one is the block diagram. As you can see in this diagram here, it could denote the entire system of a car, which might contain different elements such as a cruise controller that represents part of your system algorithm. You could have a sensor model, you could have a model of the vehicle itself, and all of these together make up this diagram. If you notice that the diagram has a lot of arrows, which means that all the information flows with some kind of direction. So the controller outputs something to your actuator, the actuator outputs something to your car, and everything follows this sequence of information. And this is also known as a causal model. That is, the blocks have cause and effect. And this is really good for modeling things like algorithms, where you're thinking of, for example, lines of code that are happening in sequence. So one line, then the next line, and so forth. Now, there's another type of graphical model that I want to talk about, and that is the bond graph. You can see it here. It's one where the components are connected bidirectionally. So by connecting two components together, there's an exchange of energy that could happen in either side. So whether forwards or backwards. This is known as an acausal model, so a model that is not causal. And this is a better representation for modeling things like physical systems, as you see in this diagram, for example, an electrical circuit, or to tie it back to our example, to model a vehicle or a suspension system within that vehicle. A little more on bond graphs, just to recap, is you can think about it as an electric circuit equivalent, where there's two types of things that are going on. You have an effort, which you can think of as the voltage of your electrical circuit. So the bigger voltage, the harder the effort on your model. And then you also have a flow, which is, again, in the electrical equivalent, a current. So that's some kind of quantity that flows through your circuit. Even though we introduce it for electrical, this has a lot of analogies that you can use for other physical domains. For example, a hydraulic system that might have pumps or valves, and it uses things like pressure or fluid flow. And also the mechanical system, like a suspension model, where you're keeping tracks of position, velocity, forces, torques, etc. And the way these work is that all of them obey Kirchhoff's laws, in which you have the current or the flow quantity has to be preserved at each node. So all the stuff going in has to equal to all the stuff going out. And finally, the voltage law, that all the efforts across a loop have to equal out to zero. So all of these deal with conserving energy. Why am I describing all of this? Well, you're familiar already with Simulink. For example, we've seen before that you can use Simulink to model a mass spring damper system. If you think about it then, you can model this as a block diagram using the standard Simulink blocks that you're already familiar with, in that all the information flows with some direction, as we described earlier. But also for physical systems, you can implement bond graph type constructs using this tool SimScape. You see here that all the components are connected bidirectionally to each other. And these are the models that Swarooph showed you. For example, in the car model, you had things like the battery being connected to a motor, or the wheels connected to a vehicle body, and so on. And the great thing, of course, is that you can combine these two. There are blocks that interface between the block diagram and the bond graph, or between Simulink and SimScape. So you can make models that contain both, physical elements and algorithm elements. And that's what you saw in the control example for the car, where the car itself was modeled using SimScape, but you also had a controller that was being modeled in Simulink. So you can imagine how this lets you create pretty large-scale system models, again applicable for things like lap time simulations. Swarooph also talked about this, the fact that SimScape is your basic foundation that contains a lot of fundamental components like mechanical or hydraulic or electrical elements. But we also had special libraries that we used all throughout the demonstrations that you showed. You had Sim Power Systems for three-phase electrical systems. We actually didn't show this one. We had Sim Mechanics for 3D mechanical systems. The suspension model was built using Sim Mechanics. Sim Hydraulics for fluid power and delivery. Sim Driveline for automotive and transmission components. You saw a lot of automotive components in that model. And finally, Sim Electronics for things like the DC motor or other electronic or mechatronic systems. So that's an overview of all these physical modeling tools that let you implement these bond graph systems within the block diagram environment. All right, so key takeaways of all these models and slides that you just saw. Again, there are two tools, Simulink and SimScape, which adds on top of it. You can combine them both, so you can combine the causal block diagrams and the acausal bond graphs, which is good for algorithms versus physical systems. And finally, with these physical system tools, you can model different types of system domains, like electrical, mechanical, hydraulic, and so on. So now, I want to hand this over to Christoph for a pretty exciting announcement.
Thank you very much, Sebastian, and also thank you very much, Swarooph, for presenting us the software demonstrations. In case you've asked yourself, how can I learn to do that? We have a really cool offering for you. So we will be offering online training. It will be available soon. It will definitely cover two parts, and these are the parts you are already familiar with a bit. So part one will deal with longitudinal vehicle dynamics and multi-domain systems. So you will learn all the skills, starting from getting to know SimScape up to the details. You can use that knowledge in order to set up lap time simulations or to predict the energy consumption of your vehicle. In the second part of that online training that will be published a bit later, we will talk about 3D suspension modeling or modeling mechanical systems, plus all the capabilities that are inside MATLAB and Simulink for design optimization? Well, you already know the use case behind. Could be optimizing your suspension kinematics towards certain events, towards certain tracks. And with these two parts, you should be well able to understand the basics of that modeling approaches and understand the basic of the tools. We're really looking forward to getting you in touch with that. The training includes exercises for you to practice, so it's both videos and also exercises for you to do. What we really like to hear is that interesting for you? And we are also keen on hearing your ideas on that. So please let us know using formulastudent@mathworks.com how you like the idea and if you are willing to take that online training. And this brings me to the end of today's episode. Yep. At that point, I can keep it rather short. You already know our feedback channel, so formulastudent@mathworks.com. Really happy to hear your thoughts on the training and on the Racing Lounge in general. Please also make use of our Facebook channel. And this brings us to the end of today's episode. So thank you again very much, Swarooph and Sebastian. It was a pleasure. And hope to see you next time. Thank you. Thanks for watching and bye-bye.